Hello, welcome to Math321. I'm going to talk about orthogonal polynomials. So I'm going to take the vector space of all finite degree polynomials with coefficients in R. All of the operations work pointwise and in the usual way that you would expect. When you add polynomials together or you multiply them, everything's exactly the same. I'm going to define an inner product on this vector space. And you can check that this satisfies the axioms for an inner product. This finite dimensional vector space is the span of this set, and so this set is a Hamel basis. The elements of this basis are not orthogonal with respect to this inner product, and you can check straight away. For example, the inner product of 1 and x is equal to the integral from a to b of x dx, x squared over 2 a b squared minus a squared over 2, which is non-zero if we're dealing with an actual interval. So if you can Graham-Schmidt this thing, you can get an orthogonal basis. So in particular, you let the x0 equal the first element of the Hamel basis. And then let xi equal vi minus the sum, k equals 1, I minus 1, vi xk, 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 xk. Direct computation, you can show that it produces an orthogonal basis. So you can do a lot of calculations with this and a lot of integrating of polynomials, and in principle everything is directly calculatable by hand, though there's a lot of algebra. So I'm basically going to skip writing it all down, but the result of applying Graham-Schmidt to this Hamel basis with this particular inner product is the Legendre polynomials. Which are rather important polynomials in their own right. So the polynomial is AB. And this can be written as some transformation with respect to the Legendre polynomial between -1 and 1, and those polynomials can be written down And lastly, the Legendre polynomials themselves, you can normalize if you wish to, in which case the normalized ones are So you can always choose different inner products if you'd like. For example, if you choose this as your inner product, which you should check is actually an inner product, it's guaranteed by this thing being continuous and positive everywhere, you get Hermite polynomials. And yet again, you can choose a different inner product. And the result are the Chebyshev polynomials. And we can check that. Tn, Tm, the integral from -1 to 1 of cos n, cos inverse x, cos m, cos inverse x, divided by square root 1 minus x squared dx. With a suitable change of basis, this ends up being and once you pick an appropriate trig identity, this is and if you work that out, the result is that you get 0 if n is not equal to m, and if n is equal to m, this term is actually a 1, and the result is pi over 2 if n is not equal to 0, and pi if n is equal to 0. And you should carefully check that that all works. So all these polynomials that you've seen, or most of these polynomials you've seen, can be expressed in this form. They're orthogonal polynomials, and orthogonal polynomials have some nice properties. But before I start talking to you about that, I'm going to talk to you about least squares. So we've been talking about interpolation. That's where the polynomial that we're building goes through our data points, whereas least squares means we want a polynomial that doesn't necessarily go through the data points, but that minimizes error. It's just a different emphasis. So here, rather than forcing interpolation and then checking error, we're going to force taking the minimum possible error. Of course, this is really some kind of inner product, and you could take any of the other weighted inner products that we had before with various factors over here, or the square underneath, or whatever. Anyway, doing that would change the emphasis on where error is allowed to be, but otherwise is a similar idea. So let's take our Qnx, and we're going to write it as a sum of orthogonal polynomials. So degree 1, degree n, orthogonal to each other. I'm going to get j equals to the value of this integral. So this thing square rooted is about the error. So minimizing this means that we can take its derivative with respect to each xi, set the result equal to 0. And if you do that, what you get out is a system of equations. Now you don't have to use orthogonal polynomials when you do this kind of calculation, but if you do, then this is going to be non-zero only when j is equal to k. And if you do this, then you quickly see that the coefficients are so if you take an interpolant for f through the data points of some appropriate smoothness, then you can express that interpolant in terms of orthogonal polynomials, and you can do this integral, then you can work out the coefficients needed for the least squares approximation very, very easily and very, very quickly. Numerically, it's a cinch. I mentioned that you can do this with alternate inner products, and usually this is called weighted least squares. W usually written there to be a particular function, which is the weight function, and we can pick that's what the inner product looks like with the weight involved. So if you take the weight equal to 1 over square root 1 minus x squared plus, so this looks like, oh well, it doesn't go through 0. Sorry, that is a minus. This means that the error will be emphasized on the edges of the interval and error de-emphasized in the middle. Of course, if you want orthogonal polynomials with respect to this, then you have to use Chebyshev polynomials. This gives you an alternate way to view Chebyshev polynomials. They're the polynomials that appropriately account for an increased interest in error at the edges of the interval rather than the middle of the interval. All of this works for discrete least squares as well. So this is probably, or might be, very much what you've seen in applications. Where the exercise run over your sample points. But again, you can follow through all the same steps as before, and you can take discrete Chebyshev polynomials. So if you take q and x equal to d0 plus d1 p1 plus, and if these are orthogonal, then the dk's end up being the sum rather than integral. And the discrete Chebyshev polynomials have this form. Shouldn't be too surprising, and the theta j's in this case, cos inverse of xj's, 2j plus 1. These are the roots, m plus 1, pi over 2. Okay, so this is when it gets a little bit better than just random facts. A nice theorem. The discrete least squares approximation polynomial Qnx of degree at most m. So we only have m plus 1 points, so degree at most m. Which minimizes our discrete norm is the interpolating polynomial. There's no reason for it to be. Well, I mean, there is in this particular case, but what I should say, there's no a priori reason why the function that minimizes the discrete norm should be the interpolating polynomial. I mean, really there is, because the discrete norm is just the sum of the function value at the point. So if you want the discrete norm to be smallest, then you want the values at those points to be smallest. So from that point of view, this isn't surprising. But this is talking about which points? So these are the roots of our discrete Chebyshev polynomials. And we have all of the properties as before, as I mentioned, because the polynomials will be orthogonal. Now there are some general properties of orthogonal polynomials which I think are very interesting and are worth going through. Just so you've seen them, because next time these things crop up, and they do crop up all over the place, you'll have some idea of where these things are coming from. So they're orthogonal with respect to some weight. Then the roots of the degree n polynomial are all real and simple, and so somehow taking the inner product forces the roots to be inside that interval. And again, I don't think there's any a priori reason why, but that's the way they are. So proof let x1 up to xk be the roots of Pnx that lie in AB. And Qr is going to be the product x minus xj. And that means that Qr changes sign whenever P changes sign. And that implies that Pnx times Qkx is of constant sign. So our inner product, which is just an integral, is not equal to 0. And that implies that Qk must have degree n. And you should think about why that is the case. Now suppose that Pnx has a multiple root. So then we know that Pnx is going to be equal for some root This is really just manipulations. So let's say it has a model root of order 2. Could be whatever order you like, but anyway, order 2. So this is always greater than or equal to 0, so that implies that the inner product of these things is strictly greater than 0. And that's again a contradiction, as n minus 2 is strictly less than n. And you should think about why. Why is an orthogonal polynomial orthogonal to everything of a lower degree than itself? Which is what the heart of this proof really says. This is a result I really like, and I think this is really cool. But anyway, any three consecutive orthogonal polynomials are related by Pn plus 1x equals ax plus Pn Bn Pnx minus Cn Pn minus 1x. And if ak, bk are the coefficients of xk and xk minus 1 in pk, then an equals an plus 1 of an, bn equals an plus 1 of an, bn plus 1, an plus 1 minus bn over an, and cn is equal to an plus 1, an minus 1 over an squared. Elementary manipulations. Okay, Pn plus 1x minus anx, Pnx is going to equal Qnx, and that's degree of most n. So our Qnx can be written as a sum alpha k pk, which means that alpha k is equal to the integral an which is Qnpk. But we also know that this is equal to Pn plus 1 pk minus an Pnx pk. Now, as claimed, every orthogonal polynomial is every orthogonal polynomial of degree n is orthogonal to every polynomial of degree less than n. So this is equal to 0. And of course that really means that Qn is equal to an Pn plus an minus 1 Pn minus 1. So if Bn equals alpha n and Cn equals minus alpha n, then we have Pn plus 1 x minus anx Pn x is equal to Bn Pn x minus Cn Pn minus 1 x. So the only thing that really remains to do is to check that the ANs and the BNs and the CNs all satisfy the appropriate equations. And that's pretty direct, because we know that x times Pn minus 1x has to equal an minus 1 over an Pnx plus something of lower degree. And that, of course, implies that Cn is equal to an Pn minus 1, which is an minus 1 over an. After you do a little bit of calculation. So now we have Pn plus 1, Pn minus 1 is equal to minus Cn, which you can check, and after you follow that through, you'll get a formula for Bn, and it follows from substitution, and you should give it a go. That is everything I think that I want to say about least squares approximation and orthogonal polynomials. Least squares approximation in a computer can be difficult to do, but if you have a set of orthogonal polynomials, which really means that you've chosen your roots carefully when you've sampled your function, then least squares approximation can be done almost trivially. some circumstances when you can choose your sample points, please do choose your sample points.